Okay, so the idea is this. For HL material, you want to focus on the concept of titration and everything that's revolving around that. And so the first thing we're going to talk about are titration curves. Okay. Remember, a titration curve involves an analyte and a titrant. And this is the known, and this is their unknown. Okay. And so when you're graphing this, you will graph the volume of titrant on your x-axis and the pH of the solution on your y-axis. And for our purposes, we'll kind of put 7 there. Now, the main two that you're going to deal with are most likely acids titrating with a with strong base, like NaOH or KOH. And so, assuming the same molarity, and the red being the strong acid, and the orange being the weak acid, assuming that they are the same concentration, the strong acid will start, actually, let me make this a little bit more we'll start off at a lower concentration. For the weak acid, it'll start at a higher concentration. And still take the same volume of base to neutralize. So, key thing, the strength of the acid does not determine how much base you need to neutralize it. So if I have 0.1 molar weak acid and 0.1 molar strong acid, if I have the same volume of it, it will take the same amount of base to neutralize it. That's a concept I think students have trouble with because although a strong acid dissociates more, both of them have the same moles of possible H+. So they will both need to neutralize the same amount of H+ before it's neutralized. Okay. And so notice the equivalence point for the weak acid with a strong base is higher than 7, and for the strong acid, it is right at 7. It's kind of hard to see the difference in color there. Let me change it. We'll do it. Yeah.
Is the equivalence point halfway of the straight line?
Yes. Halfway of the vertical, the midpoint of the vertical aspect is the equivalence point. Yeah. pH, the pH of the equivalence point. What's probably more important is the volume required to reach that. Okay? And that will play a part later on when we talk about parts of a titration curve. And then also for this one, halfway also matters as well. Yeah.
I don't know if you already covered this in the last hour, but how would the amphiprotic acids change the potential for the H+ concentration?
You won't be dealing with any amphiprotic acids here because you're going to be dealing with neutral acids, and so they aren't able to actually gain a hydrogen. So these will only act as acids. They won't act as bases here because you're adding a strong enough base that there's no chance that the acid will go backwards. So yeah, let's assume that they're all neutral acids that only act as acids. You're welcome. Okay. Oops, I didn't realize that. Questions about this? Any clarifications needed on general type? Yes, LJ.
What are you trying to show with 152 equivalence points?
You're trying to show here that a weak acid plus a strong base yields a basic salt, which means an equivalence point of higher than 7. Okay? And then a strong acid plus a strong base makes a neutral salt. That's what I'm trying to show. Yeah. So if they give you a titration curve and ask you, is it a weak acid or strong acid, like in paper 2 of our mock, you would look at the equivalence point and go, is it 7? Is it more than 7? That will be your determining factor. Yes?
You guys have a significance in the halfway.
That's going to be on the next titration curve, yeah. So this is just a basic titration curve, and now we're going to go toward a weak acid, strong base, because I think there's a lot more things that you need to know if you do that. A strong acid, strong base is fairly straightforward. There's 2 points, a start point and the end point, that the equivalence point, that's all that matters. But in a weak acid, strong base, there's much more differences there. Okay. Okay. Let's see. How do I want to do this? Okay, let's why don't y'all do it kind of, trying to figure out how to do this, just the left half of the paper like this, and sketch something like this. This is a weak acid plus strong base titration. You may want to start a new page. I think you're going to write a lot of stuff on the right side. Okay. Let's label a few parts of this here. Okay. Volume needed for equivalence. pH of equivalence. Oh, it didn't match up, but whatever. Close enough. No, it's supposed to be above 7. Because weak acid, strong base is a basic salt.
Oh,
Bless
sorry, I
you.
didn't see that this was a weak acid.
No, that's okay. Let's start with this point instead of starting at the very beginning, because this is probably the most important point to start off your equation. And so at point A, that is your equivalence point, where your moles of H plus equal your moles of OH minus. So all you have left there is salt and water. Because all the acid has been neutralized with all the base that's been added. Why is that important? Because you can calculate the unknown molarity of acid with that. Because the molarity of the acid times volume of the acid over molarity of the base times volume of the base is equal to moles of acid over moles of base, and whatever that mole to mole ratio is. couple of terms you want to know. Monoprotic means 1H plus. Diprotic means 2H plus. So if something's diprotic, it requires twice as much OH to neutralize it because it produces 2H pluses in the solution. So a couple of useful terms there. But really, the purpose of the equivalence point is just to figure out the unknown concentration of the acid. That's the purpose of that. Because you don't have enough information to just take the pH of the initial solution and figure that out. This area of the titration curve is known as the buffer region. Correct. Okay. And this is, we'll say, section B. Because buffers are a whole nother kind of thing that we need to talk about. So, the buffer region. The buffer region is an area that resists pH change when a small amount of acid or base is added. Use the word resists. Don't say the word prevents or stops, because it still does change pH. It just changes a lot less than it would be if it wasn't present. Bless you. Bless you. So a buffer has to contain a weak acid and its conjugate, or a weak base and its conjugate. So you can make buffers without titrations. That does happen. You can add like HF with a solution of NaF, because notice you have the weak acid and you have the conjugate base. Or you could add NH3 with NH4Cl. You have the weak base and the conjugate acid. You could make solutions like that. But in a titration, you end up making one anyways, because what happens is that your weak acid reacts with the NaOH, the strong base, to form water and the salt. So there's your A minus, and there's your HA, and that's your buffer. So as you add strong base to your weak acid, you neutralize some of your weak acid. And by doing that, you make the salt, the conjugate base. Anytime you have a mixture of conjugate base and weak acid, you have a buffer, because you're able to neutralize any acid or base being added.
So it's like the region before
All the acid is gone. Correct, exactly. We'll talk about that concept a little bit later. Yes, Ida?
What do you mean, like, HF with NaF? Like, are they mixed together?
Yes, they're mixed together. So if you had like NH4Cl, like salt, and you put it into a solution of NH3, you would create a buffer.
Oh, and then you add an acid or base to that.
And it would resist the pH, yes.
Thank you.
But you're making a buffer here because you're adding a strong acid or strong base to a weak acid, so you're generating the buffer part here. But that also comes with a caveat, because like Pranay said, you can only add so much base until you get rid of all the acid, and then it's not a buffer anymore. That's your equivalence point. So be careful about that. Now, as an aside for that, buffer action. Okay. Buffer action is how the two ions in the buffer react with additional acid or base. So here you have a buffer of HA and A minus. So what would the A minus react with to help prevent the pH of the solution going too high? What would A minus react with, an acid or a base? An acid. Because if it reacts with an acid, sorry, you can just write it as H plus, it will form HA, which is part of the buffer, so it's kind of buffering it. And then the HA would react with OH minus to form water and A minus. So notice that's buffer action. Because instead of allowing the H plus and the OH minus to be free, it binds to it. And that prevents it from being free, so it doesn't change the pH as much. So they work together to form each other. That way you don't notice the difference in H plus or OH minus concentration. Yes, Pranay?
So if you're like making more of the acid and then also making more of the base, does that like cancel each other out?
Yeah, usually you only do one or the other. So like you have a buffer, then you add a little bit of acid, so you make more of the conjugate, you make more of the original weak acid, so the pH goes slightly down. If you add some base, you make more of the conjugate base, so it goes slightly up. But it's not as drastic as it would be if it was just pure water. Elena.
So which one is like considered the buffer?
These two species are the buffer. But the reason why they are a buffer is because if they react with H plus or OH minus, they make their partner, which is also weak, so it can stay like that. This doesn't work with strong acids because the strong acid dissociates 100%, so there's no benefit from that. But with a weak acid, you can combine them back together and they'll actually stay that way. So they can work as a buffer. Thought I saw a hand up over here. Okay. So that's buffer action. So if they ask you to write buffer action equations, you're writing how the two species in the buffer will react with H plus and OH minus to produce the other species in the buffer.
Would they tell you to explain buffer action?
No, you can usually use equations to explain it.
Okay.
Ida.
And you have to mix those two together in the analyte?
In the analyte. Yeah.
Okay.
So HA is your analyte, and then NaOH is your titrant. They react together, and as it's neutralizing, you're making the other buffer component.
Oh, so you're like with the HF and NAF, you're making NAF?
Yes. Well, this is the easy way to make buffers. This is the other way to make buffers. So you can just put NaF salt or NH4Cl in a solution of HF or NH3 respectively, and you can make a buffer. That's one way to do it. And it doesn't matter how much of each you have. Here it does matter how much you have. Because if you add too much base to this, you'll get rid of all the acid, then it won't be a buffer anymore. So if you're going to make a buffer with a weak and a strong, the strong has to be less than the weak. Has to be less.
Kind of like an equilibrium.
Yeah, it is kind of like an equilibrium. Questions about that? Yes, Maria.
What is the difference between A and HA? Is
Okay.
Is it the proton?
Yes. So HA is our symbol for generic acid, and then A minus is our generic symbol for the conjugate base of a generic acid. Yeah, so A could be Cl, it could be F, it could be Cn, it could be anything. So sometimes when they give you like some really long acid formula, you could just write HA to substitute so you don't have to write out the whole formula. So I just keep it generic like this so you could put in any acid or base in there. But any weak acid will work with that. Or weak base. B is the notation for a weak base. And then BH plus is or HB plus is the conjugate acid. Yes, LJ?
Like the formation of the two conjugate pairs like prevents the pH change.
Yes.
Resistant.
Correct. So, because it's absorbing the H plus and the OH minus, so you can't observe it. Well, it won't change as much. I gotta stop saying you won't observe it. It will change a little bit, but not drastically. Okay. Point C on this graph. That's the initial point. Okay. Initial concentration of just HA.
How many more like, points will we have?
2 more.
Cool.
Okay. Now, we're not calculating initial concentration of HA, but I want you to think about this, okay? At the beginning, what do you have in your flask? Just all acid and water. Okay? So what kind of equilibrium are you going to have in that flask? Okay, well, what's the equation? So it's just HA and water. So what happens?
Plus H2O.
Yeah. H3O plus and A minus. Yeah, hydronium.
Do they want us to write H2O plus or?
It doesn't matter. They don't care. If you write it with water, it has to be H3O plus to balance. If you don't write it with H2O, then it's just H plus. Okay. So therefore, this is considered a Ka. This is an acid dissociation equilibrium constant.
Yo.
What? So Ka in this case equals H3O plus times A minus over HA. So this is your review of equilibrium ice charts. So it's ICE. So if you started with 1.0 molar here, you'd have 0, 0, plus X, minus X. And then 5% rule, because Ka will usually be pretty small. You're not using perfect squares here. It's usually 5% rule. Yes?
I know that there's a reason, but what's the reason so that we don't include H2O?
Oh, that's a good question. H2O is a pure liquid, and if we actually calculated the quote-unquote concentration of it, it's so high that it would mess up all your numbers. Because the concentration of water in water per se is 55.56 molar. So it would skew all your data. So we omit liquids and solids from it because their concentrations are way too high. It would mess up all our values. Yeah.
Sean,
Yes.
how do you like do an ice chart?
What do you mean? To complete an ice chart, you want to first be able to fill in the values that you know. And then the ones you don't know, you need to start putting in terms of X. So for this ice chart here, you would probably just be given this. And that implies that all your other reactions are 0. Or all your products are 0.
Why?
Because there's nothing there yet.
Okay. Oh yeah, because it's the initial.
Yeah, it's the initial.
Uh-huh.
And then these X's are relative to their coefficients.
Yeah.
And an acid dissociation base dissociation is always 1-to-1.
But the like whether it's positive or negative
Yeah.
relates to.
Well, how much you started with, right? So if you start with 0, it has to be positive on that side. So then you complete that chart all the way down, and then you use these values
And then plug it back in.
into this. Okay. Nabil.
I don't have
Okay.
questions.
Okay. I don't think they would do this on a titration curve because you're not supposed to use, you don't know what the identity of the acid is, so you don't know the Ka. But I figured that'd be a good time to say, here's how you calculate the pH of an unknown acid solution. It is kind of applicable here. I guess maybe they could say, I don't know, I'm trying to figure out what they would say. Maybe they would say, once you figure out the molarity of your unknown with an equivalence point, they might say, here's the Ka value, calculate what the theoretical pH of the initial solution would have been, and compare them or something like that.
So do you do negative log of the hydronium?
Yeah, in this problem, yeah. So you would solve for hydronium and then do negative log of that to figure out the pH.
Is the halfway point on the buffer solution with Ka?
That's what we're talking about. That's what we're going to talk about now. Okay, it's okay. It's not okay. So, okay, halfway. So this is point D. Okay. Want to make sure y'all notate that. This is the last major part on the titration curve. And then what we're going to do is I'm going to talk to you about concentrations of species, relatively speaking, because I think that's important to kind of think about as well. We did it with graphs in our notes, but I kind of want to go over that again. We got time. Yes, Elena?
Can you also quickly go over Lewis acid?
Yes, we will. Yeah. Yeah, that will be at the end after all this pH and titration curve stuff. But make sure, remind me. Okay. Here's halfway to the equivalence point. When you're titrating, you're going to have the acid plus the OH minus. Now remember, we don't ever write OH minus when we're talking about solution. We can write KOH or NaOH, but really all that matters is the OH minus. So that's why they'll write it as this, like a net ionic. Okay? And that forms H2O plus A minus, like we said before. Now at halfway to equivalence point, if we have 1 molar of this, we've added 0.5 molars of this. And what happens is all the base gets reacted. Bless you. So this turns out to be 0. Bless you. So we can complete our ice chart with that. So let me circle the things that are given. Sometimes it's in moles, but same idea. You end up with 0.5, 0.5. Actually, I don't know if I want to write 0.5 for... How do I actually want to do this? Because I was trying to... Oh, no, that's fine. That's fine. Sorry. That's fine. I was reading it wrong. For some reason, I was reading it as H3O+, and it's not H3O+. I was like, they don't all cancel out. Okay. So...
Chemistry jokes.
They don't all cancel out.
Who's dead?
Oh, no.
Why is it not like X? Didn't you just like?
Oh, okay. Because when you add a strong base to a weak acid, all the base will react. Like as you're titrating, you're assuming that all the strong base is going to react because the strong base is going to find H plus and neutralize immediately. Like strong bases don't necessarily want to be in solution if there's any form of acid present in solution. They want to neutralize. So as you're titrating, you're adding this to this, it will all react. Okay. So, oh yes, Ida.
I think you're just going to repeat what you just said, George, so I'm sorry, but why is it minus 0.5?
Because all the OH minus reacts.
How do you know that?
Anytime you have an acid and a base in solution, the strong base, or whichever one's part strong, will react.
Okay.
Okay. Now, what you notice here is that HA and A minus are the same. Yes, Sarah?
Why do we include water in this?
Yeah.
Oh, we don't. It doesn't matter. Like I put a value there, but it doesn't matter. Because I think I was still thinking of it as H3O plus, Sarah. So I put values in there, but you don't. So this doesn't really matter.
Mr. Charles?
Yeah.
When you do the ICCE,
You can do that here. You can always do CCE. I'm just kind of skipping that step. C for variable and then C for values. Yeah. So if you have these values now, guess what? If you plug into Ka,
you get
you get 0.5 over 0.5. So guess what?
what?
They cancel out.
K equals a hydronium number?
Ka equals H3O plus, which means pKa is equal to pH. Okay. Sarah Mecca. Oh, okay. So here's the thing.
Wait, what did you say?
Where the H3O plus go? Okay. Once the OH neutralizes, you have this amount of HA and you have this amount of A minus. You have to go back to this equilibrium once you do that to solve for pH. So you use this. But now we know the HA is 0.5 and we know the A minus is 0.5. So when we plug it in, then they cancel out. So That's why it's kind of important that you understand what's neutralized, and then what's left is just some HA and A minus. So now it's not, so at the initial point you had no A minus and no HA. No A minus, no H plus. But once you start neutralizing it, you produce A minus. And it's enough that it fits, you have to plug that value into your equation. Does that make sense?
Here, put that.
So this is your initial value now, Sarah. It's not 0 anymore. So you'd plug these values back into your equilibrium. So what you would do is you would now go, okay, what I have in my solution is HA and A minus. Well, I know HA yields H plus A minus. My initials aren't 1 and 0, 0 anymore. It's actually 0.5, 0, and 0.5. Because I've neutralized some of my acid to produce my conjugate base. So now I plug those in, and then it's minus X, minus X. Oh, sorry, plus X.
You basically move into a new reaction.
Yes, you move into the acid equilibrium. So then those cancel out.
Are we just kind of redefining the initial? Like, why are we, if that,
Okay, so let me say this. Up until, okay, let me try this way. Up until this point, we have some acid in our solution, agreed, right? Like up until A, we have some acid in our solution. And the acid and the conjugate base are what are in solution. So there's an equilibrium between those. Right? And that equilibrium is this.
oh, that's not just for initial.
No, I said it initial because that's 0, 0. But that equilibrium is there all the way up until A. So what we do at D is that once it's neutralized, we have that same equilibrium present, but now we have values for all the numbers. So we plug those values in, and then the things cancel out at that specific point. But in college, what they may have you do is they'll have you calculate the pH at any point here. So you would have to neutralize, take those values and plug it in and figure out the pH at any point. But for the IB, they only care about D, knowing that you know how to do that. Does that make sense? Yeah. This is actually where you could use the Henderson-Hasselbalch equation, the pH equals pKa plus log of base over acid, but we're not going to worry about that. Because this would be base, this would be acid, they're the same, log of 1 is 0, pH equals pKa. Yeah, but you don't have to worry about that. So that's the major concept that we're dealing with here. So yes, so to clarify, this equilibrium is always present until the equivalence point. Because at the equivalence point, you have no more acid, so there's no more equilibrium left. No more of that equilibrium, I should say. Because at that point, I have to be careful, because I want to... Okay, they got rid of calculation of pH of salt, so we won't worry about that. I just want to double check there. Because at the equivalence point, just FYI, at the equivalence point, all you have is A minus. Salt and water, right? So you have a new equilibrium here. You have A minus plus water yields HA plus OH minus. And that's why it's a basic salt, which is what we're getting into now. So I guess I should have grouped that with the equivalence point. But so those are all the points on the titration curve. Okay? Those are the 4 important parts of the titration curve. Questions about that before I move on to salt hydrolysis? Okay.
Ellen has questions.
Oh, Eleanor, sorry.
I think you already said this, but so it goes back to the first equation.
Yes, because that's all that's left in the solution after the NaOH is neutralized. So then it creates equilibrium with each other. Yes?
So do we need to know like all of this, or did you just use this to prove this?
I use that to prove that.
Okay, so,
Yeah, you don't necessarily have to do that.
okay.
Okay,
Thank you.
you're welcome.
But like, the values would change.
For the different type of acid, yes.
Well, yeah. So like, In that proof thing?
Yeah.
It was like 1 molar and then
0.5
0.5. But like they could give you 2
and 1.
and 1.
Yeah.
And then you could just do half of that.
Correct. Yeah. Okay, salt hydrolysis. Okay. Salt hydrolysis is when a salt reacts with water to form the original acid and base. Y'all are able to identify where a salt comes from, and so this should be fairly easy to predict. And so here's what happens though, okay? Hydrolysis of weak components have impact on pH. Oops. Because when those react, some of them will stay together. Whereas strong acids and strong bases dissociate 100%, so they don't actually stay together, so they don't impact. For example, sorry, I'll give you all a second to write this down.
So it would lower the pH?
It would change the pH. Let's not say lower, it would change the pH. It depends on what type of salt it is. So, a strong acid plus a strong base makes a neutral salt. Okay? The question is why? Because, let's say NaOH plus HCl yields NaCl plus water. And when we're at the equivalence point, you have no more HCl and NaOH left. All you have is NaCl plus water. And what happens is, theoretically, this should react with water to form NaOH and HCl. Okay? But NaOH is what kind of base? Strong. Yeah, strong base. So it dissociates. And HCl is a strong acid. So it dissociates. So did the Na really change and the Cl really change from left to right? Yeah. Wait, sorry, say it again? Yeah, they still kind of group together. So really what happens here is that all that really happens is H2O goes to OH minus plus H plus.
Why did you cross out the HCl?
Okay. Because in the NaCl when it dissolves, the Na doesn't change state. Like it doesn't change. It's still Na plus on the left side when it's aqueous, and then it's Na plus on the right side. It's called a spectator ion.
But I'm talking about like over on the.
Oh, this?
Yeah.
I was saying at the equivalence point.
Okay.
There's no more strong acid or strong base. It's just salt and water.
Thank you.
You're welcome. If you have a weak acid plus a strong base, you form a basic salt. And what happens there, let's say you have something like HF plus KOH. Yields KF and H2O.
Mr. Chong?
Yes.
Would you be asked to, or would we be asked to explain this?
Yes, using equations. That's where we're going with this. Okay. So KF reacts with water to form HF and KOH. Okay. So HF is a weak acid. Oh, it's not KOH minus, sorry. KOH. Okay. And this is a strong base. So what happens is this dissociates, but this HF does not because it's weak. So it wants to stay together. So the K's cancel out here. So what do you end up with? F minus plus H2O yields HF plus OH minus.
Oh, so it's basic.
That's why it's basic. That explains why it's basic. Because the F minus of the salt reacts with water to form HF, which is a weak acid, and the byproduct of that is the OH minus.
So in the previous one, you had like hydroxide and hydrogen ion.
Yeah,
So they cancel. So it was neutral.
right.
But here, you don't have that. 'cause
No.
it's and then
Yeah. So one of the aspects of the salt is weak, so that part actually does react with the water and stays together. Whereas a strong acid and strong base don't stay together, so they don't really participate.
Is this like at the equivalence point?
Yes, these are all at the equivalence point. Okay. Okay. Strong acid plus weak base. Let's say HNO3 plus NH3 forms NH4 NO3. NH4NO3 dissolves into Na3 plus HNO3. I'm going to break this up so it's a little bit easier to see. HNO3 is a strong acid, so it will dissociate. NH3 is a weak base. So what cancels out in this reaction? NO3. So you're left with this dissociation where it's acidic. So the ion that's from a weak part reacts with water to form its conjugate. And a byproduct of that is either H plus or OH minus, depending on which.
Can you repeat that?
Yeah. The weak part of the salt
Yeah.
reacts with water to form its conjugate. And a byproduct of that is either H plus or OH minus. That's what you want to think about. That's how you support your explanation of acidic, basic, or neutral salt.
And that determines whether it's basic.
Yep. Yes, LJ.
I get like what you're explaining, but what exactly is like the purpose of this process?
This purpose of this process is to explain why your equivalence point is above 7 or below 7. So what they'll probably do is they'll say a student wanted to titrate HF with KOH. Okay, predict the pH of the equivalence point. Well, the pH should be greater than 7 because it's a weak acid with a strong base. Okay, then they might say, state the reaction to explain your reasoning for part A. So what you would say is, well, the F minus part of the salt that's formed when you reach the equivalence point reacts with water to form a weak acid, which is HF, which also makes OH minus. That's your explanation for it.
So if it forms OH minus, that means it had to have a strong base, but if it forms H plus after, that means it
Had a strong acid, correct. And if it has both, then it cancels out. And all is left is water. Okay. I don't think they're going to talk about this too much, but a weak acid plus weak base depends on Ka versus Kb. Okay. So whichever value is stronger. Okay. So if you're given Ka and Kb, then K, the larger K is your stronger one. If you're given pKa and pKb, then the smaller one's the stronger one. Remember, because P means negative log, so it's the opposite relationship. And so whichever of the weak acid or weak base is stronger, that will determine what type of salt you have. So, for example, if the weak acid has a pKa of 3 and the weak base has a pKb of 5, this is stronger. Because in pKa terms, the smaller the number, the larger the value.
It's So that's an acidic salt.
Yes, that's an acidic salt. Very slightly acidic, but acidic salt. Okay. Just watching all the gears turn. Some slower than others.
Better than how it turned in water.
Yeah, gotta grease the gears.
Why did you?
I'm looking at Pranay, by the way.
Why is stronger and
On the
like
letter something.
equivalent?
Oh, because when I said whichever value is stronger, it depends on if you're talking about in terms of Ka or pKa. So like, I didn't want to say larger value because that only applies for Ka. I mean, yeah, Ka versus Kb. If it's pKa versus pKb, it's actually the smaller value. So I said, know what stronger means, like from earlier in the notes, then we'll use that concept.
Okay, so for the weak base, it would have to be like pKa.
pKb.
5, but like you were saying, if they were both pKa.
No, you'll want to compare the pKa versus pKb. So if they gave you the pKa of 5 of this, then the pKb is actually 9. Because pKa plus pKb equals pKw. Which for our most part is 14. Yeah. General shapes of graphs. Okay, pH axis, equivalence point, buffer region, points where pH. Okay.
Oh.
Yes, Helena.
Can you give an example if like the base, like pKb is?
Yeah, sure. Let's say you just had something like, let's say Kb was 1 times 10 to the negative 4, and then Ka was 1 times 10 to the negative 10. Well, this one is a larger value. That means it dissociates more. So that's going to be your stronger one. So be careful about whether you're talking about in terms of pKa or Ka.
So when it's pKa, it's
The smaller number, because you're doing negative log of that exponent.
On the HNO3 reaction, is the water is in a product with it?
Oh, no, because, oh, I don't know why I'm scrolling here. No, because it's implied that with NH3, there is water produced, but it's not in the balanced equation, so we just combine it together like that. With NH3s, you just combine them together. You could write it as NH4OH, but sometimes the IB doesn't like that.
When you wrote the Ka and Kb, that's just like another example, right?
Yes. That was Eleanor was asking about that.
Okay.
No problem. Okay. Questions about that? You good?
Yeah, I'm good.
Again, looking at Pranay.
Hard not to look at me.
Oh, God.
Oh my.
That was pretty good.
Hey, Steph. Hey, Steph, did Pranay bring you breakfast? Did Pranay bring you breakfast last week too?
Did you bring me breakfast?
I mean, I could have. I didn't know that was a thing.
So whose side are you on, Steph? Okay.
You shut up. I don't want to hear a word out
Okay.
of you.
Still recording. Okay. All right. The request. Oh wait, sorry. One more thing. Sorry. In titration indicators.
Phenolphthalein?
Okay. Indicators are weak acids that change color based on the equilibrium. Okay. And so what you'll usually, like you'll see in textbooks and stuff like that, they'll say like HIN for indicator for short, which is H plus and then IN minus. And so an indicator is just a weak acid. It dissociates, but it just happens to have a unique characteristic that when it's as an acid form, it's one color. When it's in its basic form, a conjugate base form, it's a different color. Okay? And so, for example, if you have like phenolphthalein, the first color is colorless, and this one is pink. Because if you think about it, when is phenolphthalein colorless? When it's in what type of solution? Acidic. Okay? Why does it being colorless make sense in an acidic solution with this equation right here? Okay? Why does it make sense that it would be colorless in an acidic solution here? Look at this equilibrium and tell me.
It's not a
Nope. Why? Take topic 7. Yeah, Nabil. Take equilibrium. Equilibrium. So why
It's
would...
pushed to the left.
Yes, right, Nabil. In an acidic solution, you have an abundance of H+. So what happens to the equilibrium? It shifts
To the reactant.
to the reactant side. That's why that side's colorless. When it's a base,
Wait, if it's shifted to the reactants, why does that make it colorless?
because that form of it is colorless.
Oh, okay.
If it's in a basic solution, the base reacts with the H+, causes a shift to the right, and that's why it turns pink. So when you're titrating, you'll notice like pink starts showing up whenever the drop hits. That's because it's changing, but then it's changing back. Because it's in equilibrium. It's trying to fight off the equilibrium change.
Like the buffer region?
Ish, yeah.
Will they
Yeah.
ask us, like, why is it colorless when it's acidic? And
Well, I feel like they could tie that into an equilibrium problem.
It's too hard.
So-
But you have to understand.
Yes, Sarah?
Explain the basic one thing.
Yeah, sure. If it's in a basic solution with a lot of OH minus, the OH minus will react with the H plus. It'll get rid of this. And when you decrease this concentration, it shifts this way, according to
Le Chatelier's principle.
Le Chatelier's principle. Does that clarify, Sarah?
Yes.
Okay. So that's what's happening with all indicators. But this is also why you only use a very little bit of indicator in every titration. Okay? Because what's the danger if you use too much indicator?
It'll skew the reaction.
Excuse your pH.
Okay, how so?
Because it's a weak base. I mean, weak
It's a
acid.
weak acid.
Weak acid.
But if you put too much of that into your titration, what's going to happen? You're going to end up titrating what?
Your
The
weak
indicator.
acid.
The indicator.
Yeah.
You'll end up titrating the indicator and your weak acid. So you notice we only put 2 or 3 drops of indicator. That's a laboratory technique thing we'll talk about in titration, that you're only supposed to put 2 or 3 drops in there, and that will be changing enough color, because if you put too much, your volume added will be off, because you'll titrate your indicator and you'll titrate your weak acid.
Can you do a double titration?
What do you mean double titration?
I don't know, like 2 things at one time?
No. You can titrate a diprotic acid where you have 2 equivalence points, but you can't like do 2 acids at the same time. Okay, and so every indicator has a pKa value because it's a weak acid, and the color change usually happens at pKa plus or minus 1 if you're estimating. Okay, the data packet does give you a value for each of those color changes. So in paper 2, you can refer to that. But in paper 1, they might just say, which indicator with the following pKa would be most appropriate for this titration? So, like, let's say you had an indicator of pKa 4, pKa 7, pKa 10, and then pKa, I don't know, 14. Okay? When would you use the indicator of pKa 4 with what kind of titration? Let me clarify that. What, Steph? And? What you didn't pick up, microphone, is Steph said strong acid and weak base. And she's right.
Are you recording this?
Renee.
I've been here less time and I already knew the answer to that question.
I announced that at the beginning of the recording session.
Why do you think you're talking to us
I don't know, I thought that was
Why
a
do you think
joke.
I've been silent this whole time? I don't want to go on the record.
Okay. So, pKa of 7 would be what type of titration?
Strong acid, strong base.
Strong acid, strong base. pKa of 10,
Weak acid, strong.
weak acid plus strong base.
Strong base.
Really, this one you're not going to really use. You're never going to use that.
Yeah, definitely.
Okay. Well, because I have to give 4 choices. So, like, you have to have 4 choices, so I just made up another number. But remember, you got to make them ridiculous enough that there's not a debate between what the correct answer is. Right? And so, yeah.
So could using indicators, not that you can't go without indicators, could that be a form of like systematic error if you're doing like a titration thing?
If they put too much.
Okay.
Yes, that is a form of systematic error. And so if they said a student added 5 milliliters of indicator, that's a significant amount enough that they would end up titrating it as well. And so that would affect your values. Yes.
Will there be a problem where you have to use an ice chart and then from that find the equivalence point and then try to suggest a
No,
indicator use?
I don't, because you don't need to find out the pH of the equivalence point.
Because I remember we had a pH or an indicator question on last year's final. I don't know if you remember that. Where it asked like what is the best indicator to use?
Yeah, but that was given a titration curve, I think. Like,
Oh.
I think you were given a titration curve and then they asked you which is the most, either the question was which was the best indicator to use or which one would cause the most error to use. And so if it's a weak acid and strong base, the one with the most error would be the one with the pKa of 4 because it would be the most far off from there.
You know,
Yeah,
systematic or systemic?
systematic.
Is there a difference?
Yeah.
Is chemistry a thing? Is it
No,
systemic? a
systemic
thing?
is not a thing. Systemic's more of a history
Yeah.
term. Okay. Questions about that? Okay. Moving on to Lewis acids and Lewis bases. Okay. I'd try to fit it on there. Okay. Bronsted-Lowry acid and bases have to do with proton donors and acceptors, but Lewis acid and base, an acid is defined as an electron pair acceptor. And a base is an electron pair donor.
We have this organic chemistry.
A little bit, yes. Now remember, Lewis acids and bases contain all possible acids and bases. It's the most inclusive of the acid-base definitions. It's not the most practical one to use, but it's the most inclusive. For our purposes and general chemistry purposes, Bronsted-Lowry is sufficient, and it's able to be measured in a way that we could understand by measuring the H plus concentration, things like that. But in actuality, Lewis acid base is the best way to define an acid or base. Okay? And all Bronsted-Lowry acid bases are Lewis acid bases. The variation comes from the idea of, well, 2 things. One, complex ions. Okay? Because complex ion reactions are actually acid-base reactions. Lewis acid-base reactions. So when you form a metal complex, like let's say CO2 plus 4Cl minus to yield Cl4 2 minus. Complex ion here. The cobalt is a metal with a positive charge. So what's it doing with pairs of electrons? Accepting them. So there's your acid. And Cl minus with its electron rich kind of nucleophile is your base.
Are you just judging that based off its charge?
That is one helpful way to do it. The general is the metal ion will always be the acid. That's a safe thing to say. Yes, Sarah?
There's no thing with like conjugate acid base.
No. That's a good question. There's no conjugate acid base in Lewis acid base. That's only for Bronsted-Lowry. Now, when these link together, they form a specific type of bond. Dative covalent bond. Good. A dative covalent bond. One where one species donates both electrons. This happens not only in complex ions, but it also happens in some covalent molecules where an atom that generally only wants a certain number of bonds has to end up bonding one more time to make everything stable. The best example of this is carbon monoxide. Carbon monoxide looks like this. Oxygen only wants 2 bonds though, so that third bond has to be a dative covalent bond, and usually draw it with an arrow to represent that both electrons are going in that direction. Oh, hand up? I thought I saw hand up. Okay. Yes?
What do you mean it only wants a bond 2 times? I thought oxygen just wants a bond like 4.
No, oxygen wants an octet, but it already has 6 valence electrons, so it only needs to bond twice.
Oh, okay.
Because it only needs to share 2 electrons to make the octet. But with carbon and only bonding that way, to make carbon an octet and oxygen have an octet, oxygen actually donates one of its lone pairs to form another bond. LJ?
Can you just re-explain the dative covalent?
Yeah, a dative covalent bond is a covalent bond where you share 2 electrons, but both electrons come from one species. That's usually from like a Cl- or any other kind of ligand, right? This is also called a ligand, an electron-rich species. Those ligands include all those species in the data packet, like Cn-, water, NH3, sorry, I said Cl- already. All the halogen ions, stuff like that. Questions? Okay. So, it looks here like you also have to include an acid is an electrophile because it wants electrons, whereas a base, we said this already, but I'm going to write it down, is a nucleophile. They use coordinate bond here. That's the same thing as dative covalent. I think they would take either one. They'd call it a coordinate bond because they call a complex a coordinate complex ion. Excuse me. The second example of Lewis acid base that is a very specific example. There's not that many that actually happen with this, but this is a suboctet central atom. That's a term I coined. That's not an IB term. So things like boron only have 3 valence electrons, so they only bond 3 times. And that's okay because that's all they have to share. But what that means is that there's an available spot for it to bond to something else. And if there is a nucleophile near it, like NH3, it will form a bond there. So what happens is BF3 can actually bond with NH3 to form this complex molecule. That looks like this. I'm just writing those dots next to NH3 to remind you that it has a lone pair. So therefore, BF3 is acting as what here? BF3 is doing what in this reaction? Accepting a pair. So therefore it's a acid, Lewis acid, right. And electrophile as well, yes. And NH3 is your Lewis base. This is a common reaction that the IB puts on multiple choice. They'll say, if you've done practice paper 1s, you'll see which of the following reactions is a Lewis base reaction but not a Bronsted-Lowry acid base reaction. So you'll look for either a complex ion formation or this formation, that's it. Every other acid base, you can see the movement of the H plus, and that makes it a Bronsted-Lowry as well. So you can't count that. So these are your two major types of Lewis acid-base reactions that aren't considered Bronsted-Lowry acid-base reactions, because there's no movement of H pluses.
And the only way to know that NH3 has a lone pair is to draw it out.
Yes.
Thank you.
You're welcome. Yes, Nabil.
That's another donation, like that's another dative covalent bond.
Yes, it's another dative covalent bond, coordinate bond, whichever way you want to say it. I'll draw the arrow there.
Will we have to draw the arrow?
Unless it states, it may state in the problem. They might say include any dative dative covalent or coordinate bonds. I would draw an arrow pointing the direction in which the electrons are being shared. You're welcome.
Wait, why do you call it sub-octet?
Because boron has less than an octet. Because boron has only 3 valence electrons, so it only bonds 3 times. So it has that available 4th orbital to bond. So yeah, I guess. No, you would say it's sp2 hybridized. You'd say trigonal planar. But it does have the ability to accept another pair of electrons. Does that help explain Lewis acid? Okay. Now, I'm trying to think. Okay, let's go conceptual here. I probably should have done this before Lewis acid base, but it's still back to titration curves. And so let's do it again kind of on the left side, and then we'll write stuff on the right side. Oops. Yeah. A, B, C, D, and E. Okay. This is not a mathematical concept. This is just understanding what's present in the solution. Yes, Sarah.
Is the group meant to be less?
Yes. Yeah. So I want you to kind of understand what species are present at each point on the graph, because I feel like this is a conceptual thing that they'll ask. They'll say, at this point in titration curve, rank the abundance of the following species in the solution. Okay? And so, at point A, no base added yet. Okay? So, at this point, what you have is, if this is 100%, you have like 99% HA and some H plus and some A minus. At point B, now you've added less than the halfway point. So here, you've used up some of your HA to make A minus, but you still have a little H plus there. That's naturally occurring in this equilibrium. So make sure that you note that this is like 50% right here. Now, why doesn't the H plus go up with the A minus? Where's that H plus going?
It's going into making the
Wait, hold on. I thought I heard it over here. It's reacting with the OH. So that's why the H plus isn't going up that much, because any OH that's being dissociated, any H plus that's being dissociated reacts immediately with the OH. Huh? To make H2O, correct. That's why the pH isn't increasing that much as well. That's okay. So, C. At this point, you're at halfway. So now, it's 100. And at that point, HA and A minus and H plus. And that's where pH equals pKa, because the A minus and H plus are the same.
Wait, could you repeat what you just said?
Yeah. So because HA and A minus are the same, when you plug it into the Ka value, they cancel out. So then you're left with Ka equals H plus, which is same as pH equals pKa. You're welcome. D is the equivalence point. So at this point, you have no more HA. And mostly, or almost all, A minus. I guess technically you have some H plus in there because it's naturally there, but really, those are the species that matter. You have only A minus and water. And past the equivalence point, oops, sorry, that got really. Past the equivalence point, essentially you've got A minus, and what are you just continuously adding in here now? Base, just more OH. So it's getting more and more basic until eventually the OH is so saturated it plateaus, and that's the maximum pH it can be. So you want to keep this in mind about when you're talking about concentration of things, because what species? That's what I would probably ask if I were the IB, to really see if someone understood what a titration curve means, like what's actually happening at the chemical level. So before any base is added, HA is water is the most abundant, obviously. Then HA, and then H plus and A minus are tied because it dissociates the same amount. When you start adding base, the HA goes up, the HA goes down, the A minus starts going up, the H plus still stays around the same point because it's making water. Yes, LJ?
Why is water more abundant than HA at like the very first step?
Oh, it's just because the amount of water you have in any solution is just significantly large. So they would probably just ask about ions. So your OH minus ion should be still 0 here. So it'd be HA, A minus, H plus, OH at step B. C, it would then be HA equals A minus, H plus, no OH. Equivalence point, A minus, H plus, no acid, no base. And then here, depends on where you are on E, it might be more OH minus, but that one I don't think they would ask about. But I think that's an important concept to understand. Yes, Elena?
Why does A minus go up but not H plus?
Oh, because what's happening is the HA reacts with the base. And so the OH minus, let me write it here. Okay. So remember, I don't know, earlier we said this is what's happening here. So it forms H2O and A minus. So notice it's not forming any H plus because all the H plus is being reacted with the OH minus. So the A minus is going up, but the H plus is not. Yeah, Ida.
For do you have the equivalence point? You listed H plus as like the second most abundant, but like how much is there exactly? Like I know it equals OH minus, but how much is there really? You know?
Wait, say it again.
I know that at the equivalence point, H plus equals OH minus, but how much H plus?
No, that's not true.
Oh wait, really?
Well, okay, I guess of the original acid and the original base, they're equal. But there is an equilibrium that's happening at that point. And so I think that's probably getting a little nitpicky here. You just want to know that at that point you have almost all A minus.
Okay.
Yeah. If I were writing a question, I'd probably do something like that because you really want to know on the macro level. Yes, Steph?
Isn't there like a way that you can move the inflection point?
Okay, actually, that's a good thing I hadn't talked about yet.
Is it in this unit?
It's okay. I think I know what you're saying, and let me ask the class and see if this is what you're talking about. Okay, what if I told you that I got a curve that looked like this? Okay. Well, of what, Pranay?
The acid.
Exactly. So the only thing that's changed here is the concentration of the acid because this takes less volume for it to react. Do y'all see that? So same curve, same acid, but concentration's gone down because it took less volume of base to react. LJ.
Wait, why wouldn't it be if the base was a higher concentration?
Oh, wait. Oh, I guess, okay. That is also another way to do it. Sorry. I had only imagined doing the acid, but you're right. LJ, you could also increase the base concentration. It would do the same thing. That's true. Because as soon as you said that, I'm like, no, that makes sense. So you could either lower the acid concentration or raise the base concentration. Either way, you would take less volume to react. That's a good point.
Wait, this is kind of like what we did last time with like the.
No, this is not rate of reaction.
No, I know, but like.
Shifting and stuff like that, graphs, yeah. Again, that's the thing. Questions on this? We've gone through a lot of stuff today. I know. Like, hopefully some of it's starting to come back to you, and hopefully it'll stick a little bit.
Like it doesn't.
Yeah.
A lot of hope in